Okay, so good morning to all of you again. The goal of the lecture today, continuing with what we started yesterday, was to try to explain how one can get this traditional result or results alike on the universal approximation that, as you may remember, in one of the first lectures, we gave a proof based on Hahn-Banach theorem. This was actually the original proof of Sivenko on this universal approximation, the fact that a combination of sigmoids translated, dilated, scaled, were able to generate an approximation of any function. You recall that it was given out of Hahn-Banach, but the goal here is to explain how it can be achieved in a similar manner, in a different manner, but with a similar conclusion in the context of control systems, right? So as we said yesterday, the different feature of the neural differential equations we are considering these days is that the nonlinearity of this neural differential equation will be given by these kind of sigmoid functions, right? Which are not very typical in the context of mechanical systems, right? So where we encounter rather polynomials, trigonometric functions, and so on, right? And we will fix our attention in particular to this sigmoid function, which is globally Lipschitz, but is not smooth, right? So good. As we said, the most prototypical, the simplest problem we could consider is that in which we are simply trying to classify data, right? So, and we said, well, we can reformulate that as a simultaneous control problem, right? So why do we say this is a simultaneous control problem? Well, we said, okay, let us consider, rather than considering a, one layer, neural network as in the original work of Sivenko, let us consider a neural network with multiple layers, and let us do it in an incremental manner, right? So this is what is called the residual neural network, in which we are moving from a configuration of the data into a different configuration of the data, right? From k to k plus 1, we are generating a discrete dynamical system that out of the initial configuration is mapping the data into a new one, in which we expect that they will get classified properly according to their labels, right? So we generate a discrete dynamical system in which, when h is a small parameter, right, we are simply making a small variation of the identity operator out of the sigmoid function, okay? But because we are allowed to choose the parameters a, b, and w, as we said, we are enjoying of all the possibilities that the sigmoid function allows, in the sense that it's able to freeze halves of the space while moving the other one linearly in, right? In the case linearly, in the case of the ReLU, right? Moving it linearly in the direction we wish, right? Then in order to establish even a more clear link with the theory of differential equations, the dynamics of differential equations and the control of differential equations, we said, if in this time discrete neural network, we assume that h is small, then we are close to the regime of the neural differential equations written here, right? So in which you see now that this is a classical non-autonomous Cauchy problem, right? So this is a non-autonomous differential equation because the nonlinearity not only depends on the state x, but also depends on the time variable t, right? The sigma, even when we consider the ReLU, is a Lipschitz function. So there is no problem in terms of the application of the Cauchy-Lipschitz theorem for the existence and uniqueness of a solution for the Cauchy problem, right? And contrarily to the linear case, right, where we look to the classical controllability problem in which you give me an initial datum, you give me a target, and then I am, I am supposed to build the control going from one to the other, but in a way that the control will change whenever you change the initial data and target. Here, we are facing a huge simultaneous control problem, right? In the sense that I am supposed to build this differential equation so that whenever I take the capital N different initial data that are to be classified, I consider them as being initial data of this neural differential equation. The control has to achieve the simultaneous goal of driving each of them to the corresponding destination. Okay? And as I said, in the context of the neural differential equations, where the time discrete dynamics becomes a time continuous dynamics, now the controls BT, AT, and WT depend on time continuously, right? So you know that in particular, we consider controls which are in L1, in L2, in L infinity with respect to time. As I said before, because sigma is global ellipses, this problem will be well posed. Okay, and this is the point of view that we developed in these two papers, right? In which, in one of them, we consider the large time asymptotics of these networks and the Turnpike property that I will explain in some of the future lectures. And in this one, the second one is the one that is more closely related to the talk today. Okay, very good. So, as I said, what is then, how do we reformulate the goal in a control perspective? We say we have this differential equation, neural differential equation, because sigma is associated to the sigmoid of the neural network. We are working in a space dimension D. D is the space in which we are classifying our objects. The objects to be classified can be very simple, and then the dimension can be, D. For instance, as we said, we are simply classifying, disks, we are just checking what the radius is, and then we can say, okay, D is equal to 1. But if we are classifying polygons, right? And we not only this, but we are also allowed to choose the color of the polygon. Of course, the dimension will be much higher, right? Because you will have to consider colors, but also shapes of polygons, right? Very good. So the dimension of the space in which this ODE is evolving, right, can change from one application to another. But of course, it's a differential equation. So the dimension D remains invariant along time, right? So in this paradigm here, you cannot reproduce, the traditional pattern of some discrete neural networks in which you jump from one dimension to another in order to reach, faster the objective of, for instance, classification or supervised learning, right? And then the parameters BT, AT, and WT. So the BT is a vector, right? So BT is a vector in RD, right? Because, we are multiplying the argument, right? We are adding the argument. And AT are in principle matrices, and WT are matrices, right? So these controls are chosen once forever for all the data simultaneously, right? So it's not like in the classical linear control theory where the control depends on the data to be controlled. So here the control has to be chosen to be the same with respect to all initial data. And of course, the number of data we may have in applications normally is large. So N can indeed be quite large, okay? Then the problem becomes quite ambitious, right? Because our goal is, given the various possible initial data in this Cauchy problem, can we find the controls BT, AT, and WT so that each of these trajectories, right? Because each of these, whenever I solve this ODE, this will lead to, to a new trajectory. right? For y from 1 to capital N, right? Our goal is to, to choose the control so that each of the trajectories gets to the corresponding label, right? Okay, good. So as we said, I mean, this is drawn not very nicely, maybe, but I think you understand, right? This is drawn here. The goal is to, make things, for instance, this will be a concrete application where D is equal to 2 in this case, right? So D, in this case, D is equal to 2. We are in the space dimension 2 in the plane. N is quite large. So we are given many initial data, right? Many data to be classified, and they are all mixed. Some of them are blue, the others are red, right? And then the goal is to classify the data so that, the blues are on the end up being to the left of the imaginary axis, and the reds to the right of the imaginary axis. I have to choose BT, AT, and WT in a way that whenever I solve this dynamical system, when the initial datum is blue, it ends up going to the left. And when the initial datum is red, it goes to the right, right? This is the kind of terminal condition. So as we said yesterday, when I compare with respect to classical control problems, I see two differences, right? The first difference is that the target is not as strict as when I am dealing with the controllability problem for a linear differential equation, in which given an initial datum and given a target, I want to get to the target. So here the targets are just these sets, right? So the left and the right side of the complex plane. So there is a lot of flexibility at the arrival, right? I just want to make sure they are separated, left and right. I am not imposing a terminal condition for every initial value, right? But on the other hand, the problem is much more ambitious because I want to control every trajectory with the same control simultaneously. And this is something indeed very ambitious that, as I said, is impossible to achieve for linear problems, right? Why? Well, because if you give me a linear problem and you try to do the same, right? This is what is called simultaneous control. It is also called in the literature sometimes as ensemble controllability. Right? Why? Because we are controlling simultaneously all together an ensemble of trajectories, right? If we will try to, to solve this problem, right, in the linear context, we will realize it is impossible. In other words, in a linear world, it's impossible to find a control UT that will be able to simultaneously, control all the trajectories. Why is that? Well, simply because of the variation of constant formula. In the linear case, the control trajectory is just the free trajectory plus the contribution of the control, which goes, as an additive term. So if you look to the map from t equals 0 to t equal capital T, this is the solution at the final time. And then you see that once the control U is given, this is just a vector, right? So this will be just a vector, right? In RD, right? Once the control is given, this is just a vector in 1D. And therefore, what this control is doing is just translating, right, the ensemble of arrival points of the trajectories, right? So then you see, if you start from, from a cloud of initial points, these are the different initial data for the ensemble control problems, we will, evolve according to the free dynamics, right? So this will produce, the transformation that the matrix A generates, right? So this will be a a nonlinear transformation, right? But then once you add the control, the only thing you will do is just a translation of the same cloud. So you see that, of course, you can always choose the control so that one of these points gets to the destination I want. But the control being the same, this translation is completely determined by one single point to be controlled, one single trajectory to be controlled. So once you determine what is the target, for instance, of this blue point being that blue point, this vector u, which is related to the control, right? So this is really the action of the control. One single point, this blue point, will determine what is the action of the control, and then the others will follow. Meaning that you will not have the opportunity to deform, to reshape this cloud anymore, right? Therefore, you know, in the linear control context, you know, in the linear control context, in the linear control context, the ensemble or so in the linear control context, the ensemble or simultaneous control property that supervised learning requires, it is impossible. Okay, so we need really to work in the nonlinear context in order to develop, you know, the applications we have in mind, right? And this is something that is very much the same as we do when we are solving the celebrated Rubik cube, right? Of course, I mean, you will never be able to solve the Rubik cube by just making translations or rotations of the ensemble of the cube, right? You really need to introduce nonlinear deformations that are able to concatenate, you know, the action over one phase while the others are invariant. It's only the fact that we are able to rotate one phase and then the other, and then the other, and then the other in a strategic manner that allows us to, you know, reorder, right, all these colors and to bring them to the desired configuration in which every phase is just occupied by one single color. Okay, this, you know, will be impossible, you know, solving the Rubik cube will be impossible for a linear ODE. Okay, very good. So actually, in this context, we can understand a bit better by saying, well, listen, let me try to understand better why I cannot simultaneously control the linear system. The reason is the following. The reason is the following. Consider again the linear problem. Right. With many possible initial data for y from 1 to n, right? And the state x belonging to Rd. How can I put this problem in the context of a classical controllability problem? Well, it's very simple. You need simply to consider this simultaneous control problem as a control problem for a huge system, right? In which the first component of the system fulfills, right, this ODE. The second component of the system fulfills the same ODE. The nth component of the system fulfills, right, the same ODE. And then, of course, every initial datum takes the corresponding, datum to be classified, right? So if you tell me about the simultaneous control of this system, I tell you, well, actually what you are doing is with the same control, right? The same control here, here, and here, you are trying to control, n copies of the same system. So what does it mean from the Kalman perspective? From the Kalman perspective, it means that, you are taking a huge state, right, which is now living in RND. Why in RND? Well, because every copy X is evolving in RD, and I have n copies of them. So the state now lives in RND. There is a huge matrix A tilde, which is generating the dynamics, and it's a matrix, right, which is diagonal, right, zero otherwise, in which you reproduce a matrix capital A in every element of the diagonal, right? So, of course, this is a matrix in ND times ND, because each of these matrices is a D by D matrix, and I have D of them. Good. And then the control operator, B tilde, is what? The control operator is just, again, being applied to U, which is in Rm, typically. If the control U is in Rm, it remains in Rm, because you see the control is always the same. This is the difficulty that I encountered. I am multiplying the number of states. I am increasing very much the dimension of the system, but the dimension of the control is limited, right? And the matrix B tilde that is entering into the system is the same copy B, 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 right? Then you can do as an exercise, right? Do the Kalman computation, right? Check the rank, and then you will see that because this system is just the repetition of the system AB, 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 in the best possible case where the rank of A and B is full, so is D, the rank of this huge matrix, of this huge system, will be D, but it will not be 2D, 3D, and D. This is what confirms what I said here, right? In the sense that the control of one single trajectory, right? The control of one single trajectory determines which control you need, and then the others will follow, but you will not be guaranteed to control the remainder of the trajectories. This is the same you see in the context of Kalman. So we really need to go into the nonlinear setting. But here we are lucky, because when we are indeed working with, the residual neural networks and the neural differential equations, the nonlinearity entering the dynamics is really nonlinear, okay? And as we have seen yesterday, right, when we really ran the simulations before getting into the theory, we just ran the simulations, and we see that indeed, the system is able to control the dynamics, right? In the sense that, each color goes to a different location, right? So this is an application, as I said yesterday, where D is equal to 3, right? Okay, so points are moving in a space. Here we see a projection into RD, right? N is large. I don't know how many points there are there, but maybe there are like 50 points or so, right? And how many labels do we have? So the capital M, the labels is equal to 3. So 3 colors, okay? And we see that indeed, you know, the classification exercise is solved very efficiently. As I said, you know, this will be impossible, right? What we are doing here, it will be impossible for a linear, ODEs. And then what I would like to explain is how and why neural ODEs, you know, succeed. How and why neural ODEs succeed. Okay. Let me try to explain this. So I will make not a complete proof. The complete proof is by induction, right? So you say, okay, you give me n points to be controlled. So the proof, right? The proof is by induction, right? So this is often done in control problems, depending on which task you are trying to achieve. Sometimes these kind of arguments are applied, for instance, for partial differential equations, where you distinguish the different frequencies of the solutions. And then during the time interval, right, you try to control the full dynamics by first controlling the low frequencies and then controlling the higher frequencies and, you know, moving step by step, right? So here we will do also an inductive argument, which, as I said, is not so, new in the context of control, but in this particular case, it is very much adapted to the goal we are trying to achieve, right? So what is our goal? Our goal is to, given a time interval 0 capital T, right? If you essentially, my remark is, this is the proof we did with Dominic-Ruiz. If you have the time interval 0 capital T, you will divide it in many subpieces that you can make equally long if you wish, right? And in each subpiece, you will control one item, control or classify one item. Of course, and this is typical in the control theory, when you are, you know, addressing the control of the dynamics in an iterative manner, it is very important that if in the first, you know, if in the first subinterval I have controlled or placed correctly the first item, when in the second subinterval I consider the classification or the control of the second item, I don't undo what I have done in the first item, right? So the question is, we proceed in an inductive manner in a way, not only that I classify new points, but I also guarantee that the previous, say, small n points that I have already classified remain classified. Okay, so you have to work carefully, because it's about, you know, dealing with a new point without undoing everything you have done before, right? Okay, so we have to handle one new, keeping the others more or less under control as well. Okay, this is the main difference in control problems. Okay, and this is what makes the control of large dimensional systems, even in the linear case, very complicated, because when there are many components on the system, right? If you try to control the system in cascade, one of the big difficulties is that when you control one component of the system, because the system is coupled, you are also affecting all the others, right? So it's not so easy for complex systems to really realize this idea that you increase the number of components you control while keeping the others without control. Okay, very good. So now let me explain you what is the main step in this classification problem. As I said, you know, the exercise is done in an inductive manner. So what I have to really learn is how do I classify one point in this cloud of points I am given. So in order to explain you what is the argument, right? I work in, you know, we are in 2D, right? So you see, we are here in 2D, in two space dimensions. So D is equal to 2, right? I have 3 labels or 3 colors, right? So I have the color blue, the color red, and the color green, right? And in this particular case, I am given n equal to m points, 9 points, right? So I have 3 blue, 3 red, and 3 green. Okay. And assume I am in the last step. So here I am really in the last step, right? Because if I will look to this cloud of points, I will say, well, you know, the greens are really in the south band. The blue are in the north band, and the red are in the intermediate band. So they are more or less classified, right? Because according to this classification, what is the classification? In this case, I have chosen to classify points by labels so that the blue should go to this upper band, the green should go to this, you know, south band, and the red should be in this intermediate band. Of course, there are many other ways to achieve this classification. I could have also divided, you know, the plane into 3 sectors and say this is the sector for the blues, this is the sector for the reds, and this is the sector for the greens, right? There are many ways you can classify, or you could have even said, no, I would like to be more ambitious. I will, you know, I will choose like 3 neighborhoods and, you know, like 3 disks. And the classification will be achieved by placing the points, right? Here, the blues to the blue, the red to the red, and the green to the green, right? But just to simplify things, I present the result in such a case where classification is successful if you succeed building an ODE, right? So here we have to build the neural ODE so that whenever you take the blue points, they will go here to the blue. When you take the green, they will go to the green band, and you take the red, you go to the red band. So when you see this, you say, well, basically I have nothing to do because, you know, the blues are essentially okay. These 2 blues are okay. The reds are okay. The greens are okay. Only 1 point is missing to be correctly classified, right? So here we have a, you see, you have a group of 3 reds that are more or less correctly classified in the intermediate band. I have 3 reds, but in the middle of these 3 reds, there is 1 blue, and the blue should not be there. So in some sense, I have to, then the goal is to build the neural differential equation that will be able to keep in the red where they stand, keeping the red in the intermediate band, keeping these 2 blue in the upper band, and keeping these 3 green in this lower band, to be able to extract blue out of this group, right? So you have to remove the blue and place the blue up. You see, this is something that is impossible to do when you are doing linear transformations, right? Because linear transformations are translations and rotations. But you see, the fact that the blue is involved, I mean, is enveloped by the reds will not change if you simply translate and rotate. So you really need to make something different, right? In which somehow the dynamics of the blue differs substantially from the dynamics of the reds, right? And what do we have? We have this neural differential equation, right? Which is evolving now. Rx is in R2, right? Which is taking, you know, at t equals 0, is taking the different points. We have 9 of them, right? And that with an appropriate choice of the control BT, AT, and WT succeeds on putting these 3 points, these 9 points, sorry, in the 3 bands that I think we have chosen to be, it was the blues here, it was the reds here, and it was the greens one here. Okay, that was the goal. Can we succeed on building this differential equation? Now, let's see what each parameter does. Right? So, AT is a matrix multiplying the state xt. So, it's basically a rotation and a dilation or compression. Okay, so the A allows me to rotate the X and then compress or expand, you know, the variable eventually in an anisotropic manner, right? So some components are pulled, you know, more than the others thanks to this matrix A. This B is just a translation. Okay. Then once you choose this B and this A, what are you doing? You are translating a space, rotating the space, compressing it eventually, and then you apply sigma. But when you apply sigma, you see the sigma is very simple. The sigma is just this. So what this sigma is doing is, you know, putting to 0 half of the space and then making sigma to be, so sigma is simply 0 to the left, sorry, is 0 to the left and x to the right. So this differential equation will read either x prime equals 0, right? Because as soon as x is such that ax plus b is negative, right? This will be, you know, 0, or this will be linear. Therefore, this will be simply either a trivial ODE in which x prime is equal to 0. So x, in that case, the initial datum is frozen, or when, you know, we are in the set where sigma is active, right? This will be just a linear function. Okay, very good. And now we just multiply by W. What is this W doing? Well, this W is simply, again, is a rotation and dilation or compression. What this W is simply doing is, you know, orienting the direction in which the linear ODE, whenever it's active, will be moving, right? For instance, in order to proceed to the proof, you realize, as you will see, that we don't need to use all the freedom, all the degrees of freedom that I am given by the B, the A, and the W. I can do it by choosing B, A, and W rather simple. The same idea as, for instance, in band control, right? So we said, you know, we can build controls that are very smooth, yes, but they are very complicated. But I can control the same system just using band controls. Here we do the same. You can take, you know, BT, AT, and WT, very smooth, very sophisticated, pointing in oblique directions, switching very smoothly. But in fact, we don't need to do this. We just take controls that are essentially of band form. They are piecewise constant, more precisely. They are piecewise constant. So in particular, you see that by a suitable choice of B, which is just the translation of the sigmoid, and the orientation of the A that allows me to, to rotate the variable X, I can, for instance, choose the equator that is, separating, splitting a space into two parts. One that is frozen because the differential equation will simply look x prime equals 0 because sigma is equal to 0 over there, right? And the one that is active, I can choose it, for instance, to be north-south, right? So I can make the choice of B and A so that the equator is horizontal, and then the southern hemisphere for the evolution is frozen, while the north hemisphere is active, okay? But as I said, this is just an example. I could take also this equator to be vertical and say that 0 is to the left, active is to the right. Or I could take it oblique and I could make, active here and 0 here. Or even in this case, I could just reverse the sense of north and south and say that is 0 here, inactive there. So you have all these possible choices. So this equator, determine, so the separatrix, the interface, so the interface is determined by B and A, right? And then once I determine this interface, which is telling me this is the inactive, so here inactive or lack of motion, and the north part will be active or moving. You see, I have chosen B and A, and with B and A, I have determined this interface. I still have the third control, which is the W. And this W, as I have mentioned before, is the one that allows me to orient the direction of the flow, of the direction of the wind in the active part, right? And in particular, I could take it to be pointing north, pointing west, pointing south, or pointing east. Of course, I could take it also in an oblique direction. But of course, an oblique direction is a little bit like a composition of two different winds, one pushing to the right and the other one pushing to the north. So all our algorithm for the control, for the simultaneous control of the neural differential equation can be developed by the composition of these simple motions in an inductive manner. Okay, so let me now explain you how out of this you can succeed on the control of this situation in which you have to take this blue point, take it out of the, of this cluster of reds, because the blue is badly placed. Here there is clearly a cluster of reds and the blue is in the middle. So you have to remove it out of this cluster of reds and place it north. Okay? So how do we do that? So we will do it combining three constant motions, right? So you will see that controlling this point can be achieved in three constant steps, right? So in the first step, A, B, and W will be constant. In the second step, they will take different values, but they will be constant as well. In the third step, they will take different values, but they will be constant as well, right? So the control here, controlling or classifying one point, Excuse me, I don't know why. One point. Sorry. Requires piecewise control constituted by 3 constant arcs. Okay. So how is this control built? We will discuss the time needed in the end, but in fact, I can anticipate what's going on about the time, right? Because you see, this equation is very nice. So this is in the context of control theory, right? Oftentimes, right, people distinguish the case where, you know, F0 is equal to 0 or F0 is different from 0. So in this case, X is the state and U is the control. We have two possibly nonlinear terms, F0 and F1. What do you think it changes in this control system, the possible presence of this drift term? So which case is somehow easier to control? The case where F0 is equal to 0 or the case where F0 is different from 0? Which one is easier to be handled, in your opinion? There is a significant difference, and it's related to the fact that when F0 is equal to 0, so F0 is equal to 0, whatever you can do in time, say for t between 0 and capital T, you can also do it, for instance, in time 1. Why can we achieve the same result, say, moving from x0 into a given target xt that I call x1? Why, if I can control, in the absence of this drift term, why, if I can control the system from x0 into x1 in time t, I can also do it in time 1? So in the absence of the drift term, clearly the control property becomes independent of the time horizon in which I am working. Why is that? Any hint? Any comment on this? It's actually very simple. I can simply proceed by scaling. Why I can use scaling? Well, because you see, if rather than working with the variable, with the state xt, I will define a new state x tilde t, which is x capital T times small t. Of course, the new state will move, x tilde will move from x0 into x1 now in a time of the order of 1, because when a small t goes from 0 to 1, the new time, capital T, goes from 0 to capital T. And then when I compute the time derivative of x tilde, the only thing I see is the capital T times x prime. So which means that if x prime was equal to u f0 x, now when you multiply by capital T, right? The new control you have is capital T times U. In other words, whenever there is not such a drift term on the control system, what you can achieve in time capital T, you can achieve it in time 1 just by taking a control that is T times bigger. And of course, you could also do it in time 1/2, 1/4, 1/8. It's just a matter of amplifying the size of a control. But if you want, you can also make it very slow, make it in time 100. You just divide the control by 100. So you see that in this case, the fact that the presence of WT is there, which is a control in the problem, allows you to ignore the issue of the time you need in order to achieve classification. You know, if you can classify, you will always be able to classify using this neural differential equation. The only thing you will have to do, of course, is pay a little bit more expensive. So if you want to classify very fast, the action of this WT will have to be amplified. If you give me more time, right, the classification task will be done by smaller amplitude controls. But the complexity of the task itself will be completely independent on what is the time window. This is why here, I don't discuss the time I need. I know that I can make it a posteriori to be as long as I wish. In particular, if you give me time 1 and you give me 9 points to be classified, I know I can classify each point in a time interval of length 1/9, so that overall, the complete time needed for classifying the 9 points will be 1, okay? But if you will give me more points, I could repeat the same argument and do it also in time 1. Very good. So this is why I focus on the explanation of the main, say, motions that are needed. It's the same as when you are solving the Rubik cube, right? What are the fundamental motions that you have to learn to implement and that will allow you to classify all possible points, right? So this is the example. The blue is here, and this is the bad location. The blue has to move to the north. So the goal in this exercise is to understand how the neural differential equation with piecewise constant control allows me to take this blue, put it in the north, but keeping this clear separation into 3 layers, north for the blue, south for the green, and intermediate for the red. So the first step, step 1, is the following. I take the interface to be horizontal and to be placed just above this blue and below these 2 red. You agree with me that as soon as there is some vertical separation, I can always do this, right? Okay, very good. If there is such a vertical separation, then I draw this horizontal line. The horizontal line is leaving the blue below and the 2 reds and the 2 blue above. So here you have 4 points. Here you have 1, 2, 5 points. Okay, good. I can always do that by choosing B, the translation, and A, oriented horizontally, so that, you know, the 2 hemispheres are above and below this, you know, horizontal dotted line. That's the first step. But as I said, once you have, you know, made this separation, you have to determine also what is the active part and the non-active part. So here the arrow indicates that the active part is the north, you know, hemisphere, and is pointing to the left using the appropriate W pointing, you know, in the direction -1 horizontally, right? So while here, right, so this south part here is frozen. What happens then if you choose the control to be, you know, piecewise constant with this B, A, and W? You let time evolve a little bit. What's gonna happen? Well, what's gonna happen is that these 4 points will move to the left. they will move to the left. Of course, as drawn here, these 2 points move to the left a bit more than these 2 points. Why? Because sigma, right? Sigma x is equal to x. So points that are bigger are moving faster, right? So in some sense here, the fact that this, say, vertical coordinate of these 2 points is bigger than this one makes that the motion of this one will be a bit faster. But the only thing I am really interested here is on the fact that, you know, after a short time, these 4 points will be to the left, and the other 5 points will be where they were, because this southern region is inactive. So after the first step, right, so I jump from here to this configuration. And then I check this configuration and I say, well, not good. Why? Because the blue is still in the middle and the blue should be in the north. Now what I can do, you know, I change a little bit, you know, the B. I change a little bit the A, and I place the equator just below the blue, right? And now I take the active region. So this one will be frozen now. The upper region will be now frozen. And the, you know, the active region will be the southern one. I will take W pointing to the left. And what's going to happen now? Well, you know, these 5 points that are in the northern hemisphere remain constant. But this red, together with the 3 green, will move to the left. And now, after the second iteration, right? So this is a step 1. This is a step 2, right? After the second iteration, you will be in this configuration in which you see, oh, this looks better because I have now 1, 2, 5, 8 points to the left of this blue point, right? Then the only thing I need to do in the third step is now I reorient the A. I choose the B so that the interface is just to the left of the blue. So I have this left vertical interface to the left of the blue. I keep this part here frozen, right? And I make this part to be pointing north. And then after a short time, what I will see, these 8 points will be frozen, located in the same place as they are here. And this blue point will move to the north, joining this interface, right? So you can play with this in many different ways. So let me give you, for instance, an example, right, where you can see what's going to happen. We can make it, we can improvise so that you see that it's going to work, right? So you could do, for instance, the following exercise. You say, well, I have a checkerboard. Well, a small one, right? And let me draw it just with, say, well, maybe should make it more symmetric, right? So I have a checkerboard like this. I mean, in reality, it should be 8 times 8, 64. So here we have only 9 small cubes, right? You could make it in any dimension. You could make it with as many small cubes as you wish. I'm just here to illustrate a little bit what we have in mind, right? And then I say, okay, I make a random distribution, right? Assume I have here nine points, right? To be 9 cubes to be filled. And then you take some red and white points and you put them in a random manner over there, right? So we can take any possible configuration. I don't know. I take something that, you know, looks like quite mixed, right? Something like this. You know, the typical configuration, right? This is quite mixed. Okay. So I have put points at random. right? Reds and green and white. So I have 5 reds and 4 whites. And when I see how, you know, these points have been distributed randomly on the, you know, on the plane, I see, oh, they are mixed. And I don't like that, right? So the question is, can I classify, right, these squares so that, you know, on the plane, right, I am in such a configuration where the reds are in the north. So maybe not very ordered, right? So I don't know. They are 5 reds here in the north. And the 4 blues are in the south, right? So this is north and this is south. Can I achieve this classification? This is the exercise I have to solve. So, and you know, of course you can do it geometrically, but I really like that you do it following the neural differential equation. Right? Okay, but now with the previous explanation, you have learned that doing it geometrically or doing it through the neural differential equation is the same. Why? Because I can proceed in an inductive manner, point by point, and then I know that the full control I need is just defined piecewise. In each piece, I classify 1 point, and maybe the classification of that point, as in the exercise we have solved before, it takes you 3 different motions, so meaning 3 different arcs, right? So total to classify 9 points will be at most 27 piecewise constant definitions of B, A, and W. And furthermore, as I have told you, you don't need to pay attention to the time window you need, because if you spend a lot of time, eventually in the end, you can compress everything to make it occur in the time interval 0, 1, just by, you know, scaling, amplifying the W. So then the point is that wherever you can do geometrically with these very simple motions I have explained you can also do it through the ODE. So let us then think on what should I do. So you forget now about the ODE, because I know that I can interpret in terms of the ODE whatever I am doing here. Sorry. So this is the configuration. So now, what is the first step? What do you recommend me to do? Do you have any suggestion? This is a very Rubik cube, right? If anyone knows how to solve a Rubik cube, this is definitely much, much, much simpler. Okay? So what do you recommend me to do as first step? I suggest the following. Let me take this interface and I put it here, right? So I know that I can always take the interface according to a proper choice of B and A and make it vertical. And then I will put, you know, the active set to the left, the non-active set to the right, where sigma is equal to 0. Because sigma is equal to 0, all this initial data, you can think on the square as being simply represented by the point in the center, right? And then you are moving all the square together with its center according to the differential equation, right? You know, all these squares to the right, these squares to the right, the 6 here remain invariant, and I push these ones to upwards, right? And then after this motion, I will be in the following configuration, in which I will have here the red, you know, I have pushed a little bit up. So this red went 1 floor up, right? And then the others, right, will be in such a configuration in which I will have what? I will have here the rest, right? So I will have 2 here and then 3 here, right? So that I have this configuration. And then I can reproduce the pattern, right? And this one will be white and then white and then white. And then this one will be red and red and red. And here it will be red again. And here it will be white. Okay, do you agree that this is the pattern I get? Okay, so now what I do in the second step, I'm not saying that this is, so this is step 1. Now we go to step 2. In the second step, I'm not saying this is the unique way of doing. Of course, you know, as it happens in the linear control systems, whenever a system is controllable, there are many ways of controlling the system. What we said, there is only one, which is the one of minimal L2, L1, LP, L infinity norm. And each of these controls is different. Once you say, I want the control of minimal L2 norm, you can characterize it uniquely. If you say, I want the control of minimal L infinity norm, you can characterize it uniquely. But there are many paths. There are many ways of doing it. So the same happens here. I don't claim that the idea of moving this first, say, box, red box to the north is the best. I just say that this is what I, you know, visualize and I suggest. So once I have done this, I say, what do I do in the second step? In the second step, I put the interface here. And I move this to the left. I can always make now the interface to be horizontal. This is the north hemisphere, the south hemisphere. The north is active to the left. The southern one is frozen. And then after the second step, what do I have? I have a red box here, isolated. And then I have the rest of the drawing, right? Which is, you know, in the south, right? Which is something like this, in which the pattern was white, white, and then white, red, and then red, 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 and then red, white. Okay, good. So you see that if the goal was doing classifying red on one side and white in the other, this is very good, right? Because in some sense that this red is isolated, and then I can use it to make different choices of the final configuration of the classification pattern, right? Because I could say that this red is in the north, and then this I choose north for the red. Or I could also see, well, red is to the left. We will see what is better. The algorithm will tell us what is better. This is the first comment, right? In this case, I give myself the freedom to classify as I wish. In any case, if my classification was finally, for instance, north-south, and you tell me, well, but I wanted left-right, then I tell you, okay, no problem. I rotate everything and that's it, right? So this is not really a problem. The problem is really to achieve the classification, separating reds into reds and white with white. You see, a second interesting remark is that when I have done the first motion, I have generated some clusters. Now you see, I have two whites here that are together, right? And then as soon as I have two whites that are together, this is like having a fat white. And the two whites are, and the two reds are also together here. And then I can work with them as if they were a fat red, if I want to. So what this shows me is that, oh, my idea that I have to classify points one by one, maybe in some cases can be improved, can be accelerated, can be simplified, because whenever I find a bunch of whites or reds together, I will move them all in one single chunk, in one single set. This will diminish the number of motions I have to produce. Okay? Very good. So what is the next motion you recommend me to do? So what would you recommend? So I could, for instance, take, certainly there are possibly better options. I could do this, and then I move this to the left, to, you know, up, right? And in the next iteration, once I will have what? The next iteration, I will have the red here, right? That will be, you know, together with blue, white and a red. And then this will be white here, red here. This has to go away. Okay, I move it up, so I have this, and then here I have white, two of them. Oh, you see, I got a full line of whites now. Okay, and then I have, oh, I have a full line of reds. It seems I'm being lucky, right? And then I have a white here. Okay. And then I take this interface here, green, and I move this, so it's here, red, green is here. I move this to the left, and after the next iteration, what do I have? I will have two reds to the left. The one that was here, right? Of course, there was one separated here already. There was one floating here. The red that I have separated in the first step is still there, right? So I will have now two reds already classified to the left, right? And then the others will be in this configuration in which I have, right? So here, 3 white cubes together with 3 red cubes, and then the white cube here below. Okay, so what is the next iteration I do? Well, I could do the following. I could take now the interface here and put the wind in the south, pushing to the east. And then eventually what I will have now is, you know, 2 reds here, 1 white here to the right. And in the middle, this cloud in which I have, you know, 1 yellow, white band and 1 red band. And then it's almost over, because now I can take this interface, push the reds in the lower hemisphere left, and then eventually I will have here 1 red, and then 3 reds together, right? And I will have the whites that are in the configuration that, you know, 2 of them are here, and the other one is here, okay? And they are separated, right? And they are clearly separated by an interface, right? That says, you know, here is red, and here, you know, is white. Okay? Okay, so you see, we have done it with 9 points. In the beginning, this looks like very complicated, but finally, how many motions did I do? 1, 2, 3, 4, 5, and 6, right? So I didn't need, you know, if I look to the original induction argument, I didn't need 3 movements per point times 9 points. That would have been 27. And you see, I started from a configuration where, you know, the mixing was maximized, because there are never 2 consecutive whites or reds. And I was able to do it with just 6 motions, okay? So then the question is, so you can think on the following open problems, right? Or questions. This is certainly related to the complexity of the motion needed in order to reorganize or solve the Rubik cube. This is probably something that has been analyzed in, discrete dynamical systems from a combinatorial perspective. But the question will be, what is, you could think on the following question, what is the maximum number of iterations needed to, to classify two endpoints. Maybe you can say two endpoints of two different colors, right? And each of them. Okay, so you can try to address the same problem. You say I have now 2n, right? I can take an even configuration like this. I have 2n. I place them. Question: how much is the maximum number of motions I need? And if this maximum number is, let's say, mn, then I ask you, okay, but the maximum number will be achieved in such a configuration in which when you put, these, say, two classes of sets randomly on the plane, maybe you reach the maximal mixing configuration like in here, right? So if the maximum number of iterations you need is capital M, right? Then my question is, what is the probability? The second question is, what is the probability that this, that the needed number of iterations is, well, you could think on mn-1 or mn-2, etc., right? Because, we are considering the worst case scenario, but very often you will be in situations where solving the exercise, the classification exercise, is much, much simpler. Okay? So it's a good time for questions. Do we have any questions? Any suggestions? So would you, for instance, do this exercise differently? Maybe you have another idea to make it simpler? Do you agree with me that if I was given different configurations, right? Like, for instance, if I was lucky enough to get maybe in this random initial distribution, I get, for instance, if I have got originally, right, from the beginning here, a cluster of, 4 reds, like this. Something that may very well happen, right? When I place randomly, reds and white, it could also be that I have gotten this configuration. Do you agree with me that in this case, things will be simpler? Yes, right? Because then I will take simply the interface here, push to the left. Then I will have a complete cube of 4 reds outside, right? together with two whites, right? And then two more whites and one red here, right? And then I put the interface here and I push this north, and I already will be in a configuration where I have four reds here to the north, right? And the rest will be here down, right? This will be this L shape of whites, and then one red. And then I will make another interface. I will push this one north, and that will be done, because I will be in a situation where I have four reds here, one red here, and then the white L will be down here, right? And then I will say that my interface is this is north, which is red, and this is south, which is white. Okay, so you see now how many iterations I did now? I did 1, 2, and 3, much less. Oh, Yao Wang has a good remark. So is about the first case or the second case? Yao, is about the first case or the second case? First case, okay, thank you. Let's see. So this was the exercise, right? Yeah. So Wang Yao says, just 9 points. I can rotate 45 degrees. And from right up, 1 red, down 2 white, and up 3 red, down 2 white, 5 steps. Okay, so I believe you. I believe you. Yes, you can also use diagonal motions, right? So what Wang Yao says, and this is very interesting, is that here I did it in 6 motions. He claims he can do it in 5. Fantastic. So you see, we were classifying 9 points, 2 colors, and I did it in 6. One says he can do it in 5. Is 5 minimal? Smart, Kai-san says, yeah. Yeah. Is 5 minimal, or can someone do it in 4? Please check. Use also the possibility that you can make rotations, and you don't need to make it Cartesian, right? I'm just making things very simple for myself. I'm not very good at this. So I'm just making things very simple for myself using just Cartesian cuts, and then, you know, north or, you know, vertical and horizontal motions, but you can make it also oblique, right? So then you can check, is 5 minimal? And as you see, you know, as soon as you will make this problem more and more complex, you can now think on a problem like this, where you are like in, you know, in 3D. So you can make it in 3D, or you can make it simply in D dimensions, right? And then you can take, you know, n to the power d points, and then you can say m, say labels, right? M different colors. You see that things will get very, very, very tricky, right? You will be in higher space dimension. You will have many points. You will have different colors, m different colors. What is the minimal number of operations you need? What are the minimal number of piecewise constant arc? Sorry, the maximal number of piecewise constant arc that you might need when the configuration is very complicated. And then what is the probability that the overall cost eventually will be much smaller, because in practice, when you put all these points randomly on this hypercube, it's very unlikely that you will be in this situation where they are really mixed, you know, with a maximal, say, mixing factor, right? Normally, you will have some clusters, and these clustering phenomena, as we have seen, produces a significant drop on the number, right? So if you want to, you can look at this, say, example. You are in d dimensions, right? You are considering, therefore, n points per dimension, n to the power d points. And then out of them, you divide them into m categories. Now you are in the d-dimensional space, so you can move in very different directions. Question, what is the maximal number of motions you will need, and how the probability of, the maximal number decreases with which probability? These are the questions, okay? So you can take this time to play with this neural Rubik cube, okay? Thank you. So does anyone have any comment or how to do it more simply? Okay, okay. So you see, something that you could observe is that when you proceed the way we did, right? When we proceed the way we did, we are getting possibly a lot of dispersion on the data, right? You could think, well, in fact, in practice, I'm not only interested on having the data, collocated each of them in the corresponding horizontal band, but I would like to have them, very well packed, right? Because, if I pack them well, then I can transport them more easily, or maybe packing also helps on having more colors, more points, and making more space for the others and so on, right? Okay, so then you see that we can also, proceed to compression after classification, right? So you see, once we have reached this configuration in which the points are well classified, if you tell me that you want to compress them, you can do the following. For instance, you can continue with the same argument and say, okay, now I take this vertical line, which is leaving all the data to the left, right? I can leave the right hemisphere invariant, and I can push the left hemisphere to the left, so that all points, this will become now, this is a differential equation in which x prime is equal to 0. So this right half space, which by the way is empty, is frozen. And this, other one will behave like x prime minus x, so it's exponentially decreasing. It means that the horizontal coordinate, the x2 axis, will decrease exponentially. So after some time, all these points will be clustering, very close to the vertical line, right? Okay, but then you could say, well, now, in the horizontal line, they are very packed. It's true, they are very compressed horizontally, but there is still, here and here, there is a lot of dispersion on the vertical, say, coordinate. Then I could, for instance, go one step further and then take this, say, horizontal line here, right? And then push the southern hemisphere to the north, while the northern hemisphere is frozen, and then all these green points will then pack, right? And once this is done, I could now take this horizontal line here and push, the southern hemisphere to the north, and then the red ones will pack also. Well, maybe when I do this, you see, I will lose the fact that the blues, the greens, and the reds are well separated, because now they will be more or less mixed in the same horizontal band. So I can restore the original, splitting by putting here a vertical line and then pushing the greens south. And then I will be in this configuration in which you see that, the packing, right, of the vertical and horizontal components in each cluster is quite good. So they are almost, you know, all coagulating on the same point, depending on color. And if you are not happy with the fact that, you know, in this operation, because I was pushing this to the left, this green cluster moved towards the left, and you want them oriented vertically, then you can take another separatrix here, push to the right, and then you will have them vertically organized. So you see that the same algorithm that allows for classification, right, guarantees also that you can achieve classification plus compression, classification plus, you know, clustering. Okay, good. So actually, you see that you maybe recognize this game. I remember that probably in China also this exists. When I was a kid, such a game existed. You know, you have a table with many small, say, squares, and then the issue was to succeed ordering them by, in particular, by numbers. And of course, in order to do this, you need one empty so that you can play by occupying this and letting the others move, occupying the free space generated by this empty slot. And then, of course, always in a finite number of operations, you can succeed on doing this, right? So there are very, very clear analogies, right? And then you see, this is how the theorem looks, right? So the theorem will say, let sigma be the ReLU, the rectified linear unit. Let D be greater than 2 in dimension 2, because in dimension 1, points cannot cross because of the uniqueness of the Cauchy problem for the ordinary differential equation. Let n, the number of points to be classified, to be greater than 2. Let the number of clusters, capital M, to be greater than 2 as well. So typically, of course, n is much larger than m. So you want to classify, so to accumulate, you know, points by features, so that, you know, the number of points of data to be classified is much larger than the number of features you have in order to perform the classification, right? And then we say, let xi be n data in dimension d to be classified into disjoint open sets, right? As I said, in our exercise, we have taken these open sets to be, you know, bands, right? But we could also do it, you know, by choosing open sets differently. So you have realized that once I am in such a configuration that, you know, the points are very clustered, if you tell me that the blue should go here, the red should go here, and the green should go here, I can continue this operation to move, right, these clusters to the corresponding destinations, right? So I can choose, you know, the final destination as I wish, right? Then in such a context, right, where you are also given the open sets, open non-empty sets, that could be a very small disk, for instance, in the d-dimensional Euclidean space given, right? So that you know a priori what is the label of every point. So this means that for every point, according to the color, you know what the corresponding, you know, target set should be. Then for every time, I know also the time doesn't really matter, because I can always compress or dilate time to fit my control classification piecewise constant algorithm within this time window. There are matrices that, of course, they are L infinity in time. Actually, they are piecewise constant. They are also in, you know, in BV, right? The class of BV. They are not continuous because they are jumping, right? But they are in BV. And the control is also in the same class, such that the flow associated to the neural differential equation, when applied to all initial data, classifies them simultaneously, so that at the time capital T, the corresponding solution associated to the controls A, W, and B will live in the corresponding target set SMI for all I, right? And then furthermore, you see that the controls are piecewise constant with a maximal finite number of switches of the order of capital N, right? So I am here, I am on the safe side. I don't know, I don't say what is the maximal number of them. I know it will be of the order of N, right? But I am not precise at this level. The controls also lie in BV because they are piecewise constant with a finite number of jumps. So, you know, they are, of course, in BV. The control time can be made arbitrarily small by scaling. The complexity of controls diminishes when the initial data are structured in clusters. This is what we have seen in the previous example, right? And the complexity of controls also diminishes when the control requirement is relaxed so that not all data need to be classified. Of course, if you will tell me that, you know, out of all the data, you are only focusing on the classification of a few, you are ignoring the others, so the capital N is diminishing, and therefore the number of operations you will need will decrease as well, right? And then you say that the target SM can be just N distinct points in the Euclidean space, right? So you can basically, actually should be an epsilon neighborhood, right? So it could be the target SM can be just epsilon neighborhoods of N distinct points in the Euclidean space. Okay. Oh no, see, if the points are distinct, you can even, you know, put them right in distant points. Okay. So then you see that this is very much also related to other concepts like Voronoi diagrams and so on. You could think on all these kind of links, right? So you could think on whether, you know, the complexity problems we have considered, right, is related to other concepts like Voronoi diagrams, right? So actually, if you think on the complexity, right? If you think on the complexity, so the impression we get is that, you know, when you give me, for instance, red points, and now I draw it with blue, otherwise the white will be invisible, right? What is, in your opinion, how would you characterize the complexity of the algorithm we have developed for such a configuration? In your opinion, how you will count the number of motions you need in order to achieve the goal by the algorithm we have given, which is very much adapted to the neural ODE, right? You could say, well, Enrique, you did it in a very particular manner. Yes, but I did it in a way that, you know, the neural ODE understands very well, because the neural ODE likes to do this, right? When sigma is equal to 0, frozen. When sigma is equal to identity, you know, trivial exponential motion of the ordinary differential equation. So now, if you give me a cluster like this, where I see blues and reds mixed, how do you think I could characterize the complexity of the algorithm I will need, the maximal complexity of my algorithm, right? Do you have any suggestion? Any comment? It seems to me that if we are doing so, the number of motions that we will need is somehow related to how many hyperplanes I need to separate points, right? Because you see, if you do something like this, right? Right, something like this, and then something like this, and then something like this, and maybe something like this, and then something like this, and then something like this. That's fine, right? So it seems to me that in some sense, when I am doing such a drawing in which I am counting how many lines, right, there are to separate points. So this seems to be giving us, right, the number of iterations I will need in our algorithm, right? So then the question, another question will be how the complexity of the controls we need is related to the number of hyperplanes needed to separate points by labels. Okay, of course, I could have more colors and then I will need more hyperplanes, more points, then more hyperplanes. But this seems to be really the criterion, right? More than how many points there are, because you see, here I have 3 points, or I could have many more, but I will not mind, right? Here I could have many more, but they will all act as a single, you know, fat point that can be moved. All the cluster could be moved simultaneously, right? So it seems that this kind of, you know, number of separating hyperplanes, which seems to be very related to classical concepts like support vector machines and so on, you know, could be, you know, the right tool in order to analyze the complexity of the algorithm. This is, I mean, there is plenty to be done there. There is plenty to be understood. So in our you know, result, what we say, listen, there is something important ongoing, and is that something that will never be able, you know, be possible for a linear differential equation, for a neural differential equation, occurs and is quite, you know, straightforward. Once you understand the principle, it's very easy to understand, right? So, but now please recall what I told you before. Oftentimes, when you are dealing with complex dynamics, and this is a complex dynamics because although the neural differential equation is rather simple, you have many copies of them, and you need the same control to be able to control all the trajectories, as you know, this kind of drawing that we said, you know, this drawing that was impossible for linear differential equations, we have succeeded doing it for nonlinear, you know, neural ODEs. As I said, please keep in mind that this is just a result saying that, you know, there is such a control. Okay. Now I could ask you, can you characterize the control of minimal L2 norm doing this? Can you characterize the control of minimal L infinity norm doing this? Can you characterize the control of minimal L1 norm doing this? You could ask all these questions, right? And then you will get different, say, controls. Actually, right, when we do the video, we have the impression that the motion is very smooth, right? So it doesn't look like, you know, the video is using controls that are jumping, right? In which, you know, the dynamics will be much more like a zigzag. This is quite smooth, right? Why is that? Well, because in this exercise, right, these are simulations that were done by Borjan Geskowski. Rather than drawing the video of the proof we have done, what we do is just solving an optimal control problem. This is the optimal control approach I mentioned yesterday in the end of the morning session. I said, listen, you can do the controllability, right? For this, you need to understand the Kalman rank condition and the adjoints, and it's quite tricky. Or you can just do the optimal control strategy. This is what most people do when they are facing, nonlinear problems in mechanics and so on. I mean, Navier-Stokes is too complicated to be, handled using Kalman. It's infinite dimensional. Even the substitutes of Kalman on a PDE level are not so easy to manipulate at a computational level. So people just prefer, okay, let me do the optimal control approach. What the optimal control approach was, okay, you give me controls. The controls are A, W, and B. I put them all into a, say, big vector, U, right? So this is a matrix n by n, this is n by n, this is n. So the dimension of this vector will be depending on time, right? So this will be a vector U depending on time with a dimension that will be 2 times n squared plus n, right? Because I have, here matrices and matrices, n squared and n squared plus n. Then I will minimize a functional in which what I'm doing here is I am penalizing this control, for instance, in H1. Why not? I could also look for it in L2, but I can also make it to be in H1, because then I will have better regularity of the trajectories, better compactness properties if I have to pass to the limit, whatever the parameter for, passing to the limit is, right? Sorry, here maybe it should be rather not n squared, but d squared, right? So if we do it in dimension d, it will be d. N is the number of points, right? N is the number of points. So now what I do is I penalize the distance of the solution at the final time, right? With respect to the given targets, right? That I put here in a vector notation. Otherwise, I will have to put a sum, right? And I can penalize either just the arrival point or the integral all along time. I will discuss this in a future lecture. And it's when doing such a minimization that I see that, probably the algorithm that, that the computer looks for, which is characterized by an optimality system, right? Is characterized by an optimality system will be, will be more smooth than what we have done, in our construction. And then I will get videos like the ones we have seen, right? For instance, you see here in 3 space dimensions how, we are in dimension d equal 3, right? We are in dimension d equal 3. The number n here is quite large. I mean, you see many reds and you see many blues, right? But you see also that the dynamics is quite nice. I mean, it's very smooth. It's quite parsimonious, and it's successful, right? Well, we said it's successful. Is 100% successful in this case? So do we really succeed on separating all reds from all blues? Or you see some defect on here? I know I could do it, right? But maybe the control will be more complicated than the one is underneath this video, right? Do you think this video shows a perfectly successful classification, or you see some defect? There is an obvious defect here, right? There is this red point that is embedded into the blue cloud. So this is not perfect. Why is that? Well, because I repeat, in this video, I'm not drawing controls which are exact and are so sophisticated as they are in my construction of the piecewise constant controls that are succeeding into a full classification. What I'm doing is just, minimizing a functional in an optimal control approach in which I am making a compromise between making the control not that large and, enhancing the classification that is required so that each point goes to the corresponding destination according to the label, the color here, blue or red. So if I want to enhance, the classification pattern because there was a defect here, right? So, or maybe this is a different video. Let's see which one, if this does it correctly. No, you see there is a defect here as well, right? So there is a defect. This red is not well placed. If I really want this red to go down and the blues to remain up so that, the classification is not, say, like here, 99%, but is really 100%, so that there is a clear hyperplane that separates red and blue, what I need to do is what? I will need to work more. I will need more control. I will need a control U that is larger. And in order to get a control, right, U that is larger, what I will need to do with the parameter alpha? What do you think I need to do with the parameter alpha if when I run the simulation, I see that the success rate is only 99% and I want to enhance it? What should I make with alpha? Should I take alpha bigger or alpha smaller? Small alpha. Thanks. Yeah, thank you. Thank you both. Thank you, Cheche. And yeah, so there are actually 3 answers, right? Thank you all, right? Han, Che, and Yao. Thank you. Yeah, alpha is smaller. Why? Because, when I, rather than minimizing J alpha 1, I minimize J alpha 2 with alpha 2 smaller than alpha 1, then the tendency of the control will be that the norm of the control U2 will be larger than the norm of the control U1, because you see, when I minimize alpha, right, I decrease alpha, what I'm saying is that I pay less attention to the size of the control. This is like if using control will be cheaper, right? It's like when if the electricity will be free, then we will probably be consuming much more electricity than when electricity is expensive. Then you pay more attention to how much electricity you are using at home, right? The same with the gasoline in the car. So if alpha 1 goes down to alpha 2, the size of the control U2 increases, and then, the performance of U2 will be greater than the performance of U1. Right? That's natural. Okay. And this is what we expect, and this is what actually we see, right? So you see the 2 results are purely compatible, right? Why is this result interesting? Why, if I can just do the optimal control approach, right? Why, if I can do the optimal control approach, I need such a result? Why should I be concerned with such a theoretical statement if I know that I can proceed computationally and achieve something that is quite good? And if I need something better, I can make the alpha smaller to improve the output. Why do you think such a result is important? Well, such a result is fundamental to know that you can achieve full classification, right? What this result is telling you is that maybe it's very expensive, right? Maybe it will take many, many switches. Maybe it will take a large norm, but you can actually achieve classification, right? You can always achieve classification. Therefore, if you are knowing that this result is true, if you are working computationally just, using the classical optimal control approach, minimizing functionals in which you are penalizing both the size of the control and the distance to the target, you know that if you really need it, if you really need to get very, very close to full classification, but making alpha smaller and smaller and smaller, you will succeed, right? Otherwise, you will be always hesitating, like in the linear case. Otherwise, you will be in the same dilemma, right? What is the dilemma? The dilemma is that even in the linear case, just to explain it more simply, right? Right? If, right, we don't know whether the system is controllable, right? How can we know whether, right, the distance to the target can be made smaller than epsilon, right? Because as I said yesterday, when the system is not controllable, this is like this situation in which one component of the system, X1, is driven by one matrix, the other component of the system is driven by another matrix, A2. A2B is controllable, right? But within the state X1, X2, S1 is not controllable. And you are in such a situation, right? You will never be able to go, to the target beyond a given threshold, because the gap, the error you will have on the components X1, you will never be able to reduce it. This is why, right, it's so important to know that AB is controllable. If AB is controllable, then you know that you can push this epsilon to go to 0. So even if you are not really interested on the ultimate controllability property, knowing that the system is controllable is what allows you to guarantee that when you will apply a straightforward, say, optimal control strategy, this will bring you as close as you need to the corresponding target. Just give me a second, please. I have to. Sorry for the interruption. So now let me explain you something complementary, right? Because you could say, well, we are a bit confused, right? Because Enrique was making the theory for linear problems very carefully. But now when we are in the context of neural networks, we are working systematically with nonlinear problems. So what is the link between the theory that we have developed for linear problems and the nonlinear problems? Because in nonlinear problems, I can also look to the two issues, right? So one is controllability, and the other one is simply optimal control, right? So what would the problem will be in this case? Okay, now, for instance, you give me a nonlinear differential equation. I could make it to be a partial differential equation like a nonlinear wave or Navier-Stokes or heat equation also. The ideas will be the same. Of course, you will need to be embedded in the context of the functional analysis, because then solutions are not vectors, but just functions in some functional setting, right? You can assume that, so xt is the state, right? That is living in RD, or I mean, if you wish, maybe in Rn, and then the control U is the control. And then you tell me, oh, I want, you know, the solution to get close to a given target. Okay. You can assume, for instance, that F is globally elliptic, so that there is a unique solution globally defined in the interval 0t. I avoid all the discussions related to the possible blow up of solutions or the possible lack of uniqueness of the solutions that will add complexity to the problem. This is not the point we are trying to make here, right? So if this is your goal, right? If this is your goal, how do I proceed? Well, I could discuss the problem of controllability. I will do it later, right? But assume I'm just interested on the optimal control strategy. What I will do? I will say, for instance, then, okay, I minimize a functional, which is the norm of U, you know, in some space, plus the distance to the target that I can penalize here with a constant K, right? K over 2, 1 over 2. So I minimize with respect to U. And then the first question you realize, because, you know, the control is entering non-linearly on the system, because it's part of the nonlinear function, right? This could be, I don't know, it could be the logarithm of x times the sinusoidal of U. It could be nonlinear on U. The first thing you wonder here is, you know, in which norm I should minimize the control. I penalize the control in which norm? You like to have a norm here so that at least when I look to this minimization problem, you will be able to say, well, there is a minimizer. So what is the proof we are going to do for showing that there is a minimizer? I will apply the direct method of the calculus of variation. I will say, well, wherever the space X is, I don't really mind, right? Which space I choose, X, I will put the norm in X, and therefore the minimizing sequence will be bounded. If X is a Hilbert or a reflexive space, the sequence will have a converging subsequence. This converging subsequence J of controls will lead to a sequence of solutions. And I would like to pass to the limit on the sequence of solutions. But you see, this is nonlinear. And passing to the limit on the nonlinearity is always tricky, even impossible. We know the limits are not often what we expect if the convergence I have here is simply weak, say, in L2. So I better have a strong convergence in L2, right? This is why it's very natural to penalize here, right? You will penalize rather than, you know, working in L2, you will work in some Sobolev space, sorry, H1, for instance, right? You don't need the Sobolev space H1. Any any amount of information on the holder continuity with respect to time of the controls will suffice. You could take a solid space HS with S between 0 and 1. But okay, things are getting then more complicated. So let us just do it in H1, right? And then here you will do it in H1. Okay. So then because of the compactness, so H1 0T RM embedded, compactly in L2 0T RM, you will see that this implies the existence of a control. Yeah, okay. Optimal, so I should say optimal control, which is the minimizer of this function. Okay. So then the next question I ask is, will this minimizer be unique? Sorry, is the minimizer unique? Normally, yeah, Jan says that I should also maybe impose some L1 condition for a sparsity, right? Yes, but you see, if you do it in L1, then you will not have compactness, right? Okay. Okay. So is this functional convex? Because when you are dealing with the minimizers, frankly, the only way we can guarantee that a minimizer is unique is when the functional under consideration is really convex, right? Because if the functional was not convex, something like this, well, then sorry, I think you are not seeing anymore, right? Something happened. Let me share again. Okay, sorry. I think you missed some comments, written comments, right? Okay, so I said the goal is to get to xt. I will penalize definitely the distance to the target, right? So this is the norm simply in the arrival space Rn. And I said I penalize here with the norm H1, right? Because I need some compactness to prove the existence of the solution, right? If you take here a norm in L2 or even in L1, which is true, is good in order to guarantee a sparsity meaning that the control is acting only in a few time instances, then I will have some difficulties to prove compactness, right? And maybe the existence of a minimizer will not be guaranteed, at least by standard methodologies, right? So just to make sure that I have existence of the control, right, I will impose a penalization on the control in H1 that I know by Sobolev embeddings that is compact in L2, and this suffices to pass to the limit to say that the solution associated to the limit of the controls is the minimizer of the functional, right? And then I said, question, is this minimizer unique? And I said, well, you see, basically the only way we know to guarantee the uniqueness of the minimizer is to, ask the functional here, this is J of U, right, to be convex. Of course, I mean, this is also a situation where the global minimizer is unique, right? In here, the global minimizer is unique and the functional J is not convex. Yes, but I mean, if you don't have convexity, for us, it's very hard to say whether there will be a minimizer, because it could also be that the functional not being convex, the two, local minima are global minima, and then, the uniqueness of the minimizer is not guaranteed anymore, right? So the existence of the control is easy to prove once you take a functional that is coercive and compact. The uniqueness is much more tricky. Well, but you see, when I look to this functional here, a square, my feeling is that it should be convex, right? It's just the sum of two squares. Cannot I guarantee then that the functional is really convex, and therefore the pathologies of these drawings here is removed because, you know, really the functional is something like a parabola with a unique minimizer, right? So the question is then, is J of U convex? What do you think? Is it convex? Well, of course, the function that U gives you the square of U, of the square of the norm of U, is a convex function. This is fine. This is actually strictly convex. Of course, the you know, the norm square is also convex with respect to X. But here we are not looking to the convexity with respect to X. We are looking to the convexity with respect to U. And what can I say about the convexity with respect to U? Right? I have to look to the map that to U in the space H1 is giving me xt in the space Rd. And this map, you know, is computed through resolution of this nonlinear differential equation. So this map here, you know, is nonlinear and actually quite complex. So then, because of this, the map that to U associates the norm of xt minus xd squared in Rn, no reason to be convex. Okay, you have to be very careful about this, right? Yeah, so thank you, Ma. Not convex because F is nonlinear, completely correct. This is the point. One has to be very careful. It looks like nice because it's just sum of squares. One says, oh, it should be complex. Be careful because this as a function of U, you have to check the composition of this square with the mapping from U to xt. And you see, when you compose, composing, you know, be careful, right? Composition is badly behaved for convexity, right? Okay, take a function phi, right? Which is convex. Okay. And now take another function h that goes from Rd into Rd. Smooth. Can I say that phi composition H is convex? When can I say that phi composition with H is convex? I know phi is convex. This is given. And this is very smooth. But I don't have any idea what is the shape of H. Yeah, very good. So it's only when H is linear, right? So the answer is yes, but only when H is linear. Which in our case of this differential equation, when is the mapping from U to X linear? When is this solution map from U to the solution X linear? Is only when I am dealing with a linear system, right? and the control U is appearing on the right-hand side as an additive term. Okay, so then in general, if you proceed by this optimal control approach, basically forget about uniqueness as soon as the system under consideration is nonlinear. People will tell you, I don't mind. My goal is to find one optimal control. I know the one optimal control is optimal already in the sense that is the best possible. So why should I think on other, right, minimizers? This is the kind of answer you might receive. In fact, it's not completely true, right? Because you see, if my goal, right? Yeah, so the point is that uniqueness is not totally irrelevant, right? If the goal is to minimize, for instance, xt minus xt, so there could be two controls, u1 and u2, so that the norm, the combination of the two norms is the same, right? The combination of the two norms is the same, right? But actually, maybe the norm of U2 is bigger, and therefore this one is smaller. So it could well be that depending on, you know, how the two global minimizers are, one of them is better than the other, right? With respect to the final target. And of course, the better one will be the one of, you know, higher norm in L2. Of course, it could well be that the two ingredients are balanced, you know, the two ingredients in the functional we are minimizing are balanced so that the two controls are identical with respect to this combined criterion, but so that one of them is better for the final objective if I only consider the objective of getting closer to the target, right? So it's not totally irrelevant whether there is uniqueness or not. But it's true that we can give up to uniqueness. We know it will be very hard to achieve as soon as the functional is non-convex, and this will be lost as soon as the functional, the nonlinearity here is, the nonlinearity in the ODE is nonlinear. So we give up. So here you see I have penalized the two terms in the functional to be minimized differently, right? So this is actually a functional j depending on k. So if I want to get closer and closer to the target, so to make this final distance smaller, what should I do with the k? Should I take it larger or smaller? If I want to push the distance to be smaller, should I make larger? So if I make k large, right, this is like pushing, you know, the distance to the target to be smaller. By the way, you realize that making k large is the same like taking here a 1 and putting here over k. Because, of course, if I here, from the previous functional in yellow to the new functional in red, the only thing I have done is to multiply the exit, the output, the value of the functional by 1 over k. So the minimizer is the same. Of course, the value of the functional has been divided by k, but the location of the minimizer, the u, the control u I get is always the same. So, and this is precisely the alpha that I have written in our slides about the optimal control in these video simulations done by Borja and Geskowski. He was penalizing differently. He was taking here an alpha, but it's the same, except that, of course, you know, if you call this alpha, k large corresponds to alpha small. overall is just according to common sense. You know, the term you are penalizing more is the one that is more relevant. Okay, good. So now I repeat, be careful, non-uniqueness because of the lack of convexity. Actually, why can I see that there is a problem about the convexity of this composition? Even in 1D, what is the characterization of the convexity in 1D? How can I check that easily that a function in one space variable is convex? Any suggestion? How can I check that a function in just one space variable defined on the real line is convex? Second derivative, very good. So I compute the second derivative, right? So what is the second derivative of phi h composed with phi? It will be, you know, the first derivative of the first derivative. The first derivative is phi prime at h times h prime. And when I take the second derivative, I will get phi double prime h times h prime square plus phi prime h double prime. Oh, so I have two terms now, 1 and 2. This one is very nice, it's positive, right? Because this is the second derivative of phi. If phi is convex, the second derivative is positive. H prime square is fine because it's the square of the first derivative. I don't mind the sign of the derivative of h. The square will be always positive. So this is positive. On the other hand, if h were convex, h double prime will be positive as well. But is phi prime positive? Is it true that a convex function is always monotonic increasing? Is a convex function phi monotonic increasing? Sometimes it is, right? Sometimes it is, like the exponential, right? This is convex, and this is monotonic increasing. But the parameter is convex, and of course it's not monotonic increasing. So you see that this is a problem, right? So then what you can see is that, you know, phi composed with h is convex when both phi and h are convex and h is increasing. Sorry, phi is increasing, right? You can also, as we said before, right, phi composed with h is convex when phi is convex and h is linear, right? Why? Why is, if h is linear, I can guarantee the convexity. I can guarantee that this second derivative is positive. Yeah, because h double prime is equal to 0, right? So if, you know, when h is linear, the second derivative goes away. And then, you know, this second term disappears, and therefore this one is always positive, right? Okay, so, but these are basically the cases where I can guarantee that. And of course, this evaporates as soon as I am dealing with a nonlinear differential equation, because, for instance, you know, yeah, I will not know whether the dependence of the solution on the control will have any kind of monotonicity property, and this is very unlikely, right? So typically, you will be in a situation where, right, you can apply the optimal control approach, you can get an optimal control. The optimal control will be, you know, good. Normally, you will make it better and better by taking k larger and larger because you will be enhancing, right, the target. But yeah, but it will be hard to say whether you get, right? So the optimal control approach right? So the comment about the optimal control approach, the optimal control approach will lead to control UK such that, xkt minus xt decreases as k increases, but it will not tell us how close we get from, being really close to the target. Of course, when the system is controllable, we can guarantee that the condition can be achieved. Okay, this is why it's important to know also whether the controllability can be achieved, because otherwise, as I have said before, there could be a substantial component of the system which is non-controllable, right? And so that whatever you do, you penalize a lot the component, the constant K, but you will not improve, right, the final output, right? So this is the same example I have done of the non-controllable linear differential equation by blocks. You can, of course, do it also in this case. You could have a first component of the system to be completely, right, independent of the other component and of the control, right? Have, the second component to be depending on the control, right? Right? And then you see that whatever you do, right, regardless of how close, how big you take the K and how sophisticated and large is the control, well, you can do whatever you wish on X2, but you will never succeed on controlling X1, right? So this understanding of whether the system is controllable or not is important, right? And precisely what we have done with this fundamental result, right, that the one we proved with Dominic, is to guarantee, listen, when you are in the context of the neural ODEs, because of the very properties of the sigmoid function, you have this controllability property. It's magic, right? This is something that is very hard to achieve for nonlinear problems. You can, maybe we can discuss this in a later class. You can discuss the controllability for nonlinear problems, but it's very tricky. You can use linearization arguments, and then you will get local results. You can use Lie bracket arguments, and you can get some geometric proofs. But the fact that, you have this simultaneous controllability property is something that is quite unique, right? And this is also, there is an independent paper, right, that, by Andrei Agrashev and Sarichev that I recommend you also, where, they use Lie bracket techniques to prove similar results. Of course, because they use Lie bracket techniques, they will need, the sigmoid to be smooth, right? But this is not so relevant after all, right? Because, the proof we have done with Dominic here, I have shown you the proof for the sigmoid like this, right? The ReLU. But of course, if you will take a ReLU, which is a little bit regularized, the same proof will work. Why? Because overall, we are trying to get to open sets. And getting to open sets is an open condition. You will make a small variation of the nonlinearity, and you will still have it. Okay. Good. So you see, in principle, our proof, even though it's done for the ReLU in order to simplify the presentation, right? You can also do it for smooth cases, right? Actually, because the arrival condition of getting to an open set is open, as I said, also what we did with piecewise constant controls, right? You know, we use controls that were piecewise constant. Of course, in that case, you could also regularize a little bit the controls, right? And you will still preserve the conditions, right? So because the final target we have, right, is open, you can make small variations either on the sigmoid or on the controls and you preserve, right? I see there is a very interesting question by Yao Wang, right? So, I mean, this is indeed, I was planning to talk about this in another occasion, but we can maybe briefly discuss it today in the remaining minutes, right? So the question is, what can I say about the controllability of the system? So you see, in the Neural ODE case, we were very lucky because you see, I made the proof of the controllability, even for the simultaneous controllability, something that is exceptionally true only for, you know, these Neural ODEs involving the nonlinearity given by the sigmoid, the ReLU. And I was able to do the proof by a geometric argument about the Rubik cube, right? Just these combinatorics of the puzzle of the, you know, of the reds and the whites that everyone has understood just by very simple motions, right? Piecewise constant, cutting, translations. Everyone has understood the proof without getting into any theory, right? How can we do some theory for the controllability of nonlinear systems? Well, as usual in nonlinear analysis, the first you can do is to say, okay, if I have a linear theory, for controllability, and you give me some nonlinear problem, I can certainly do something by nonlinear local deformations, right? So the first argument is, so the first methodology, which is the simplest, is the linearization. How does the linearization work? Well, I give you just one example, right? The linearization goes that way. I say, okay, I will use small controls. If I use small controls, this is the first thing I should do, right? Why understanding how, you know, large controls will, you know, affect the dynamics if I am not able to understand what the small variations of the controls do. This is what we do, right? So why? I mean, this is like when you are driving. So I mean, you don't take a big car, a new car, and drive very fast. So you first learn how to drive this car, and once you feel comfortable and you know how this car is responding, you will maybe increase the velocity, but only when you are, you know, you are safe, self-confident that you know how to drive this car, right? So what does it mean, linearization? Linearization means I take the control u equals 0. And with the control u equals 0, right, I compute one trajectory. Okay? This is just the free trajectory, the trajectory in the absence of control. This will give me a trajectory that I will call x bar of t. Right? This is just a consequence of the existence and uniqueness of solutions of this ODE. If f is globally ellipses, this trajectory exists. Okay. Okay, so now basically what you say is that, well, if U is small, right? Now I take controls of a small amplitude, right? Then you could think that the control U is like epsilon V, right? So the control being small, I can think on having a small parameter, penalization parameter epsilon. And then, of course, if in this nonlinearity, you modify U from 0 to epsilon V, what you expect is that the new trajectory X will be what? Will be the original trajectory X bar times Y, right? And then how are going to be related, you know, the V, the control you are implementing in a small dose, right? And the Y, right? The variation of the trajectory you will get out of the reference trajectory X bar. Well, I write simply the ODE and I say the time derivative of X bar S bar plus epsilon Y is equal to F of X bar plus epsilon Y times epsilon V, right? And now I will do a Taylor expansion of this nonlinearity out of epsilon equals 0. So this will be F X bar comma 0 plus F X, the derivative of the nonlinearity F with respect to the X variable at, say, X bar comma 0 times epsilon V. So epsilon Y. So I will get an epsilon here, and I will get then epsilon FU at X0, 0 times V, right? And now when you check, oh, okay, of course I will have here a second order term, right? But in the implicit function theorem, in the inverse function theorem, in the Banach, I mean, in the Banach contraction, I know this, you know, quadratic term will become negligible when epsilon goes to 0. And now you come here and you say, oh, but the time derivative of X bar, right, is equal to Fx bar 0. And then I get an epsilon here and an epsilon here and an epsilon here that I can remove. Therefore, you know, for Y, what I have is simply the ODE, right, like this. Right? And then I say, oh, but because X bar is given, right, this is a given function of, say, T, and this will be a given function of also T. So I see that when I'm trying to do nonlinear control out of a reference configuration, for instance, for control U equals 0, where I can, you know, build the reference trajectory, what I am led is to the control of a linear system where now A and B are time dependent. So excuse me a second again, today too many people are knocking my door. Just a second, okay? So how do we handle this? We see, oh, in fact, I was hoping that out of the control theory we have developed using Kalman, I could do the local perturbation argument to deal with nonlinear small amplitude control. But I have here, you know, coefficients depending on time. Both, you know, the dynamics is driven by a time-dependent matrix, And the control operator is also time dependent. So it's not immediately, right, applicable what I learned before, because AT depends on time and BT depends on time. Well, not always, because you see, when I have said that I linearize the system around 0, if X bar was a steady state, then it will be fine, right? So you see first that, you know, actually, you know, the classical A-B Kalman rank controllability theory suffices to get local controllability of the nonlinear system around a steady state. Okay, so this is the first remark. Why? I repeat, because among the trajectories along which I can linearize the system, the fact that these trajectories depend on time has an impact on the linearized system, in the sense that the linearized control system is not autonomous anymore. The matrices A and B for the dynamics and the control depend on time. If I linearize around a steady state, it doesn't happen, and I am in the A-B context. So I can say that if A-B fulfill the Kalman rank condition, then the system will be locally controllable, right? Okay, small variations only. You will tell me, well, maybe you are not interested on small variations, right? So I'm sitting on my office chair, right? So this is a steady state configuration. What does it mean, local controllability? It means that I can, out of this steady state configuration I'm sitting, I can rotate a little bit and continue sitting, right? So a small variation. Maybe you are not interested on this, right? Maybe I would prefer, I have to go from my office, I have to go to the library to look for a book. And this is on the basement, right? So it's you know, we are in the 3rd floor. I mean, the library is on the basement. I have to go down. This is not a local control around this steady state. This is a large deformation, right? Okay. Then, of course, when you are moving along a trajectory xt, this is much nicer, right? Because you are making small variations, but the small variations will, you know, will lead you to, you know, to the destination of this reference trajectory. So you will be moving along the trajectory, right? So it's like, you know, when you are on an airplane, yeah, I am in a steady state configuration. I can make small rotations just to watch a movie or read or write on my computer or eat something. Yeah, but I'm traveling, you know, 1,000 kilometers per hour. In 10 hours, I am in Beijing. So that's why it's so important to be able also to control along reference trajectories that are time dependent, because then I enjoy the transportation that spontaneously this reference trajectory do. And what I make is small corrections in the end, right? So I take my airplane to Beijing, and then in Beijing, I take, you know, a taxi or a bus to go to the hotel. This is the local control, right? But the big motion, I have enjoyed profit of this. So how do I consider the controllability of this linearized problem? Of course, the Kalman rank condition as such, it doesn't respond to the question. I can, however, apply the duality theory, right? The duality theory applies. Because then I simply consider this a joint problem, right? And the only thing I need is the unique continuation condition which says that, you know, if B star t, phi t is equal to 0 for all t, right? Then phi t is equal to 0. This is what I need, right? Okay. That's the only thing you need to check. Okay, so this is not that bad because, for instance, you could think on cases where, for instance, the nonlinearity F is analytic. If the nonlinearity F is analytic, I mean, you can expand it in power series expansion. The solution X of this problem depends analytically on T, right? Because X depends analytically on T, the functions AT and BT will be analytic. And therefore, you know, you could use the same arguments as we used, you know, in Kalman to say, well, if BT and AT are analytic, everything will be expand in power series, and then you will find some kind of, you know, Kalman rank condition, which is more tricky, of course, but you will get it, right? So you can see that, for instance, you know, both in the book of Sontag, right? Eduardo Sontag, and also in the book of Jean-Michel Coron, devoted to the control of ordinary differential equations, right? And then basically, I mean, you can still go farther because you see, once you have done local control, right? Right, you can also glue patches, right? Sorry. And then you can make bigger deformations also, right? And this is actually what we do, right? So when I go from on vacation from one town to another, right? Very often, you know, I don't go direct because maybe here actually, you know, there is a lake and I cannot cross it, right? There is not a bridge. I will rather decide to visit from here to here, from here to here, from here to here, from here to here, and from here to here. And then each of these jumps maybe will be a short trip I can do in one day. I can even do it maybe with my bicycle in 2 hours per day or so. Then I visit one village and then the other and then the other. And you see how by making small jumps, right? Then you can guarantee that you can go from any place to any place, right? However, right? However, these arguments might need a large control time. In here, in the local argument I have done here, the control time can be arbitrarily small, right? Why? Because after all, I'm using just linear theory, the adjoint, the reduction to, you know, analytic theory, then power series expansion. I can do everything in a short interval and I will get the controllability on a short interval. Of course, you know, when you try to go to the nonlinear, the shorter is the time, the smaller will be the neighborhood you are controlling the trajectory. Now, when you start patching this to do a small, from small to large deviations, then it could be that you need a large time. This is precisely what we discussed today. If you are giving me a system like this with drift, even in the simplest case, you cannot guarantee that the time of control will be small. But there are many control systems, in particular those in which this drift term is not present, and the control is multiplicative, as it is the case in the neural ODEs, for which once you know that the nonlinear system can be controlled maybe in long time, then it can be also controlled in an arbitrarily short time. Why? Because you simply, you know, increase the size of the control. Then this means that if there is a path joining this city and this city along this trajectory, what I'm telling you is that if there is no speed limit, you can go as fast as you wish. But as you know, normally there is a speed limit, right? There is a speed limit in the highway, I don't know, 120 kilometers per hour. And then maybe you can take the fast train, but there is also a speed limit for the fast train. Will not go beyond 300 or 400 kilometers per hour. So there will be a minimal time. So this is something you have to be ready to pay. The fact that for nonlinear systems, there might be a minimal time of control, okay?